Whoa, wasn't ready for that. Good afternoon. My name is Jim Sorensen. I'm a senior principal engineer at Amazon. I've been at Amazon for about almost 8 years now as part of the team that actually built the original version of S3 way back when. And so today, yes, we're going to be talking about S3. And since this is considered kind of an advanced discussion, I'm going to make a lot of assumptions about what you know about S3. So, for example, S3 has buckets in it, and you store your objects in buckets, and the keys are the names that you give your objects. And a lot of the things like that, we'll just kind of assume that we know. And then we'll be talking about some of the more advanced topics of S3. So when I think about S3, having worked on building it, I think about it probably in a completely different way than you do. I think about there's this billing subsystem, and there's a part for doing repair after when disks fail, and there's the whole request processing part of S3. And to you guys, I suspect that you think about it like a tool. It's just this thing that you use. And so I found a picture of this thing. This is a Beckman-Eaton laminectomy retractor, right? And it's a very specialized tool for doing back surgery. But when I look at it, I think probably about the only thing I could use it for is to serve salad. And so, if you have this tool, this very specialized tool, and you don't use it right, you're not going to it's not going to perform for you the way you might need it to. And S3 is kind of the same way. To get the high performance, high scalability out of it, we have to use it correctly. So this talk is about using S3 and making it scale. And scaling is a kind of in the eye of the beholder, right? Each of you out here probably has a very, very different use case for what scaling means. Some of you probably have millions or even billions of objects. Some of you may not have a lot of objects, but you have really, really large objects, and so your scalability to you might be bytes. Others of you probably have lots and lots of users, millions of users coming in and either putting data or getting data from S3. And then there's just this bandwidth thing. How do you, are you moving lots of bytes in, lots of bytes out of S3? And these things all overlap, but they're all different dimensions of scalability. So in today's talk, what I want to do is cover essentially 10 mini talks of different things that you can do to get better performance out of S3. We're going to spend a bunch of time talking about how to do hashing of keys and why this is important when you have when you're managing lots of objects. A little bit about lifecycle policies, again, for managing lots of objects. Multipart Upload, a feature of S3 that's great for dealing with large objects. Object aggregation. A very specialized use case, but if it fits your use case, it's a really great way to save money, move data quickly. We'll talk a little bit about content distribution, server access logging and how to turn that on and why. Some things about bucket policies and how you can scale uploads to S3. Pre-signed URLs, an extension of that. And then we'll talk about two networking subjects, DNS and Time to Live, and a little bit about window scaling, unfortunately, like a network lecture. So let's start with hashing of keys. If my timing is right, it's, I'm off by 2 minutes, darn it. So a lot of customers store objects in S3 and give them names like this. So, here I'm showing a customer is uploading data, and they're assigning keys at the current time. So 2012, November 29th at 15 or 3:06 in the afternoon, and they just assign names like this. So you can see how, or with the dates, and there's a problem with that. And if we assign the names like this, we get performance problems and capacity or request processing problems. Let's look at or talk about why this happens, because the best way to understand why something like this happens is to kind of understand what's happening under the covers. And to do that, we need to think about some of S3's features and kind of how S3 had to be built. So there's three key features that kind of drive why this is an important issue. And the first is S3 has no objects per bucket limit. You can put 1 billion objects in a bucket. You can put 10 billion objects in a bucket. There's no limit. The other key thing that we have, or feature that we offer, is that you get to list the contents of your bucket. And we give you this lexicographical ordering of what's in your bucket. And then the last thing is it's fast. And what I mean by fast really is that it's real time. We don't go out days later and make a list of your objects. If you put something, you expect it to be in the list if you turn around and list it. So we have to be fast when we do the listing. So one possible solution that S3 could have implemented for building the index on S3 is we could have done something like distributed hash tables. And you think about it, this has some really, really nice properties for building or for storing objects, right? It scales well. We add more hosts. We can distribute the objects around. So what I'm trying to represent here are some customer with yellow circles and all their objects, and some customer with their reds or orange stars, and so on. But a distributed hashing actually won't work for S3. And the reason that it won't work is because we have this requirement that we allow you to list your objects. And so if we have, in this example, 5 hosts, but if we have hundreds or thousands of servers, and your keys are distributed over all those servers, if we want to list your object, maybe we could enlist the resources of the entire fleet of machines to go look up your objects. But when your neighbor wants to do the same thing at the same time, obviously we're going to have a problem. So distributed hash tables is not a viable solution for partitioning S3's keys. So maybe we could partition by bucket, right? This also has some really nice properties. It gives us isolation. All of the yellow customers' keys can be in one place. And so now listing gets to be much easier. But this violates our requirement that we allow you to put as many objects in a bucket as you want. Because if I build a partition and you put 1 billion at some point, whether it's 1 million, 1 billion, at some point that partition is going to be full. It won't be able to be on a single host or however you want. However, that partition is actually implemented. So what do we really do? So here's kind of how S3 does its partitioning. And I kind of show this rainbow here. This is kind of to represent your key space, the things that are starting at A or however you're naming them. On the left in red and going through time to the purple. So the problem is, if you use a key naming technique like the date-based one that we were showing, what happens is all your puts end up hitting that logical partition in one spot. And this partition has finite capacity to take requests and will overload this partition. The other thing that happens is this partition will continue to grow, and at some point, S3 has to split it off and put it someplace or break the partition. There's a couple of problems with that. One is that if you're naming your keys and you're putting lots of objects in this partition, when we do decide to partition, we're going to be competing with you. You were trying to drive this partition as fast as you could to get your data in, and all of a sudden now we come along and we say, hey, you've got way too many keys in this, we've got to split it up. So now we contend with I/O, and you get a bad experience. So so we need a solution to this problem. And one of the solutions we recommend for you guys is, you can continue to name your objects like this, but what we want you to do is add some entropy to the keys. And what we're showing here is I've taken that key name, the date along with the customer ID, and computed a hash, an MD5 hash. And I take 4 digits from the end of the hash, I believe it was, and assign that to the prefix of the key. And what this does is it allows us to insert the keys with more entropy into the space. So let's go back and look at our kind of partition space. Now, when you're inserting, instead of having just the capacity to put into partition D, we can put into partitions A through D. And for this particular customer, they've essentially quadrupled their capacity to put data into S3, the number of requests per second that it'll support. Now, as time goes on, these partitions will continue to grow, and we still have to, at some point, maybe in this case, partition C got full, and we've decided for whatever reason it might be that it's time to partition it. Now we're in a much better position, S3 is in a better position to do this partitioning because you're not contending with the I/O on that partition in the same way that if you were doing it all in one spot. So when we do this partition, you probably won't even notice that it's happening because your load is now spread across all these partitions. Another common technique that we see customers naming their object, and it's the exact same problem, is that they may use a sequence number, like say from their database, the index column from their database, a monotonically increasing sequence, and name the object and put them in S3 like that. One solution that's, I don't know if we want to call it clever, is to reverse those digits. Move the entropy towards more towards the prefix of the key, and now when you store those objects, they get spread over the partition. One point that I should make about this is that, I should give guidance as to when is this something that you need to do. And our guidance for this is that if you're putting less than 50 objects per second away, you don't have to worry about any of this. Just continue to do whatever you want to do. We have sufficient capacity to handle that load, no problem. If you're doing over about 100 objects per second, putting objects per second, you really need to start looking at this because it will give you much better performance. And if you're in that 50 to 100 requests per second, you probably should look at a scheme like this because, first of all, if you're at 50 to 100, it doesn't take much to go from 100 to 200, does it? I mean, customers come and go and so on. And it's just a better long-term scaling solution for you. So really above 50 requests per second, one should look at a naming scheme like this. Okay. So, lifecycle policies. Recently, S3 launched the object archival policy, which is integration with Glacier. Hopefully you guys have a chance to attend one of the Glacier talks. The object archival is a way of transitioning your objects from S3 into Glacier and then paying the Glacier storage rates. This talk is really more about scalability, and so I want to get back to the idea of having lots of objects. And in that realm, object expiration is really kind of important for this. So if you're managing millions or billions of objects, actually deleting them can be a troublesome task. So what we've implemented about a year and a half or so ago was the object expiration. And the idea here is that you set a policy on your bucket to have S3 automatically do the object removal for you. And so I'm showing an example of a single rule for a bucket. And there's kind of three key pieces of information here that we concern ourselves with. The first is we allow you to name this policy. So, this is essentially just information for you. Here is my 30-day log object expire rule. There's two pieces of information that S3 needs to operate on. One is a prefix. These are the set of keys in your bucket that this rule will affect. So here I'm saying anything in my bucket that starts with log / will be affected by this rule. The slash is kind of important. S3 doesn't really have directories and file directories like a file system has. It just has names. So if you said log and then you put something in your bucket that just started with the word log, like, I don't know, logger.jpg, that object would be affected by this rule. So it's important to put the slash. And then the other key piece of information that you have to tell S3 is how long do you want these objects to stick around for? And in this case, we're saying for 30 days. So one of the things that that customers will use this feature for too, that's kind of neat, is like if you have a bunch of thumbnails, say, and you decide I need to resize them, rescale them, and then you want to get rid of the old ones. And say you have millions of these thumbnails. What you can do is rescale them to a new bucket, put them in the bucket when you're happy with the outcome of that transcoding. You can turn around and put a 0-day lifecycle policy on the original bucket, and S3 will take care of the cleanup for you. And as soon as the lifecycle policy goes into effect, we quit billing you for those objects, and we'll delete them in the very near future. So one of the things about, So every feature that we have in S3 is accessible via the API. There's some REST call that you can make to set up the lifecycle policy. Or you can go through something like our the AWS Management Console. And this is just a screen capture of me setting up a lifecycle rule in the console. Much easier way to do the one-off thing. Once it's set forever. Next, I'd like to talk a little bit about Multipart Upload. So Multipart Upload is a feature that's been in S3 for about a little over 2 years now. And before we had Multipart Upload, you know, if I had a big object and we could store up to 5 gig objects without Multipart, what you'd have to do is start at the beginning of your object and, you know, kind of walk through it, uploading it to S3. And more often than we would like, and I'm sure that you would like, these transfers for some reason would get aborted. And then you'd have to start over again. Not a great experience. So that was one of the motivations for building Multipart Upload. It also lets us store much, much larger objects in S3. And the idea is that you simply take your object, your big object, and you logically break it up into some number of pieces. Now, we really recommend that you do about 100 megabytes per chunk. It's a reasonable number for if you have to restart, and it lets you build, you know, relatively large objects. The Multipart Upload will support up to 10,000 parts on a Multipart Upload, so you can actually get really large objects using this. The other really nice thing that Multipart gives you is if one of these parts does fail its upload for whatever reason, you simply have to reconstruct or re-upload that single part, and at the end then assemble the object from there. So it lets you recover from failed puts much nicer than the original scheme. Another thing that Multipart does for us that we couldn't do before in S3 is allow you to store objects in S3 before you know how large they are. Typically, when you do a put, you have to include the content length into the request that you send to S3. But using Multipart, what you can do is, say I'm building a log file, a large log file, and in this example, I've shown that I've already uploaded 2 of my chunks, or parts, and I have 3 in progress, and I don't know how long this object is going to be. But I have to know how large each chunk is. At the end, when I say, okay, this log file is finished, maybe it's at the end of the day, whatever it may be, I assemble the object, and at that point, S3 knows how big your object is, and will store it off away. So another nice feature that Multipart will give you. Another tip or trick that one can use, and this is kind of a specialized case, is this idea of object aggregation. If you have millions and millions of objects and they're all relatively small, there's a couple of problems that can happen. Well, not really problems, but it can take a really long time to upload these. And then there are upload requests. You have to pay for a request for each object that you upload. So if you have these objects and say they're fixed size, so maybe 1K, for example, what you can do is you can aggregate those together and put them into one large object. So say you have 1 million objects and they're 1K, that object would be 1 gigabyte. That's not an unreasonable size to upload. And then you can take that aggregate, or you can use Multipart Upload again to upload these objects and store it in S3. Once it's in S3, because, and again, I say this is a specialized use case, but it's actually relatively common. For example, spriting on a web page would be one of the ways that you might take advantage of this. But you can pull that object out of, using range get, out of the middle of that aggregated object. So now you've only paid for the put request for a single object, but you still have your millions of objects accessible as individual objects. You just need to use range gets to get them. So again, kind of a very special use case, but really awesome if you can take advantage of it. Moving on. Content distribution. Lots and lots of customers use S3 for content distribution for all different kinds of use cases. And you know, this is a typical histogram of the popularity of an object for content distribution, where the y-axis is showing how many times the object was fetched, and the x-axis is your number of objects. And so this is a very typical curve. Lots of objects are fetched frequently, and then you have this really long tail of objects that are fetched less frequently. And S3 is really, really good to use down on this part of the curve. You know, if say the object is fetched once a day or once, maybe even once an hour, you know, it's the kind of thing that would be served well from S3, because even if you put it in front of CloudFront, if it's aged out of CloudFront's cache, it has to go to S3 to get the object anyways. So the first fetch from CloudFront is actually slightly longer. So, but CloudFront is really good to use on this part of the curve, where you store your content in S3 and put CloudFront in front of it. So for the really popular objects and the very cacheable object, this works out as a really good solution. And so, you know, if I was running a large medical supply place, I could imagine that surgical gloves are sold quite frequently, and my Beckman-Eaton laminectomy retractor, if I had to learn how to use it, I was going to use that picture more than once, would be less popular and probably would be a good object, like image to store in S3 versus the more popular content. Another reason why you might want to put CloudFront in front of, or use CloudFront, is that if you're sensitive to the latency that it takes to get objects from S3. So, for example, the round-trip latency from Seattle to Washington, D.C. is typically about 68 milliseconds. It varies sometimes depending on the internet and how the routes are set up, but this is about a typical round-trip time. If you're sensitive to that, you know, 68 milliseconds can be a short period of time for some people, and it can be a really long time for other customers. You know, CloudFront is a good solution then to use. These stars are just showing some of the POPs or points of presence that CloudFront has in the US. It gets you much closer to your customers. Server access logging. There's not a lot to say here, other than you guys should turn it on. Server access logging is like the Apache access log. It's got a little bit more information in it about like bucket owner and things like that, so that we can guarantee we're sending these access logs to the correct customer. But they really can help you debug your problems, and they're invaluable for us if you are experiencing problems. There's request IDs in those files that we need to look up to assist you in debugging problems. Here I'm just showing a screen capture, again, from the management console, where we're setting up bucket logging for my particular bucket. Apparently my example log bucket is no longer available. I own it. And what we're doing here is just saying the prefix is where the S3 will write the logs for this file. Next, bucket policies. So bucket policies is a fairly rich access control management system that you associate with each of your buckets. And what it's really good for is granting access, or a great use case for it is to grant access to, say, your partners, where you set up a policy that would let your partner put objects into a certain bucket, or you may have an outgoing bucket where you allow your partners to get the data out of the S3. And the reason that there's a couple of things. I talk about partners here, and the reason that I say that is, you know, when I think about partners or our business partners, you know, we typically don't have millions of them. We have thousands of them, maybe. And you can have up to 1,000 policies or rules in the bucket policy, and you can have 100 buckets per account. So you can really set up and manage up to about 100,000 of these policies for your buckets. So if you have millions of customers, this technique isn't going to work. But the other thing that's really nice about it is once you grant access, you don't have to manage the credentials on your partners. They just have to be AWS customers. They have their own credentials, and you just identify and say, hey, you know, you have access to, in this case, my incoming bucket. Another thing that's really nice about doing the bucket policies is you can allow your partner access to put or get from a bucket, and delegate or have that partner set up IAM users for themselves, and they can manage those keys and the users and still have access to the bucket. So now you can scale even beyond those numbers of partners by using the IAM users. So the other problem, though, is sometimes you have customers, millions of customers, and you need to make this work. And pre-signed URLs is a great way to do that. So here's a typical case where you've got many, many customers, say there's millions of customers, and they're trying to upload data into S3. So they would come through the internet, and at that point, once the traffic arrives at your service, you need to have a fat enough pipe to be able to take all that inbound traffic from all your customers and send it to your service, and then you need another outbound pipe that's just as fat to send it back out to the internet and get it to S3. Now, you could run this service inside of EC2, but you still have a problem, and that is that you have to have enough EC2 capacity to support that fat pipe into the EC2 instances. So, if you're doing gigabits of traffic per second, you're going to need a lot of EC2 instances to take that traffic in to proxy it down to S3. So one possible solution that we absolutely do not recommend, but kind of gets the concept across, is that you could take your key, your access credentials, and send them off to your customers, right? They could sign the request, and you'd obviously do this all in JavaScript inside browser pages or something like that. You wouldn't expect millions of people to actually start writing code to interact with the API. So you could send them these keys, they could sign the request, and now they make the request into the internet, and the only fat pipe that we have to have is that fat pipe to S3, which we already have. So a really good way to solve this problem is to have your service generate pre-signed URLs. So inside the customer page, you embed this URL that's signed with your credentials that allows the customer to send the request to S3 that says, hey, I want this object stored with this particular name in my bucket. You own the object. You actually can set up the access control policies in the pre-signed URL, and so on. And so all you need now is a really, really thin pipe to your customer to say, hey, this is the pre-signed URL to use. So a great way to scale large uploads to S3. Next. DNS Time To Live. This is an issue that Bytes customers more often than we would like, and so I want to make a point of this is one of the things that hopefully you guys walk away from this talk with and remember it, and it's not just applicable to S3. But a couple of key points. Well, first of all, S3 has many, many, many IP addresses. And these IP addresses come and go all the time. We're upgrading software and we may take some IPs out, or there could be power failures on a particular room or whatever. And these IP addresses come and go, and we're managing weights and things like that. Another key point is DNS resolution is cached. The ISPs cache it, your services cache it, so it's cached all through the request path. S3 actually publishes our DNS TTLs at 60 seconds. So what that means is that if there is a problem on an IP, for about 60 seconds, it's possible that we would be serving that DNS address up, and it would be unavailable. If we make the time smaller, most ISPs don't honor the TTL. If we make it longer, you get a worse experience. So 60 seconds is about the fastest we can time these out. And then the other point is, S3 has a service SLA. We have an availability SLA, but we don't have an SLA on our IP addresses. So it's really important to remember that. And the reason I bring this up is that Java, in particular, is really bad about this. They have this caching behavior, and there's a system property called networkaddress.cache.ttl. This is taken directly from the JVM documentation. And they set the default to -1. That default of -1 means cache forever. And the reason that this is bad is that let's say you have a Tomcat server that's running your site, and you upload data or get data from S3 in this Tomcat server. You can be running for weeks and weeks and weeks, and our IP addresses has been stable. Your Tomcat has cached that IP, and then we, for whatever reason, need to do maintenance on that particular piece of hardware, and we take that IP away. You will see S3, or your Tomcat server will think S3 is down because it's trying to talk to an IP address that is giving you connection refused. So I think this was a mistake to make this a default behavior, but it is the default behavior, and you need to be aware of it and really set that value to something more reasonable to stay out of trouble like that. So let's see. So the last thing that I was going to talk about today is TCP window scaling, and this is not something that's unique to S3. Window scaling is kind of a tricky thing to get right, and I'm going to turn this a little bit into a kind of a networking lecture. So the networking engineers have this concept of this thing called a bandwidth delay product. And what that is simply the product of the speed that your internet connection is going and how far away the receiver or the transmitter and receiver are. So in this example, if I have a T1 line, which moves data at 1.54 megabits a second, and they're 100 milliseconds away, the delay, the bandwidth delay product is about 18.8 kilobytes after you convert from bits to bytes and to divide by 1024. So not a very large number. If I have a fat pipe and I'm relatively close, say I have a 1 gigabit LAN and I'm 1 millisecond away, the delay bandwidth is 122 kilobytes. And to take it to the extreme, if I have a 1 gigabyte with 100 milliseconds, I could put almost 12 megabytes into that pipe, or the delay bandwidth. So why is this important? This is a diagram of a TCP header. And the thing I've highlighted in pink or orange, I guess whatever color, is the window value. And it's a 16-bit quantity. So 16 bits allows you to store a number between 0 and 65,536 or 64K. And what that number is how much data the receiver is willing to, or the transmitter will be buffering, waiting for ACKs from the customer. So again, why does this matter? So if I have a big fat pipe and I'm a good distance away from my customer, I can, with a window of 64 bits, I can put only 64K of data in the pipe, and I have to wait for that to get transmitted all the way down and for the acknowledgement to come back from my customer before that data, before I can start sending more data. So in this example, I have a 1 gigabit link, and the best I'm going to be able to transmit data through, because of the distance, is 640K. Not a very efficient use of this resource. So, and when the internet was made, 64K windows, that was a huge thing to do. Today, there were quite a few years ago, they came up with this concept of TCP Window Scaling. And what that means is that when two sockets initiate a connection, they negotiate at the beginning of the connection during the SYN packets a window scale. And that window scale says, hey, instead of being 0 to 64K, I'm going to actually shift it in this case, 6 bits left. And now I can support a window of 4.19 or 4 megabytes window. I highlight the 6 because 6 is actually the TCP window that S3 advertises out to you guys. And at 4 megabyte, that allows us to say on a 100 megabyte pipe, we can have our customer 335 milliseconds away and keep that pipe full. If they're a little further than that, well, we will start stalling the connection again. But at 335 milliseconds, that's pretty much all the way around the world. So it ends up working out quite well. So the one question that you might ask, though, is, why do we set it at 4 or when the window scale at 6 instead of something larger? And the reason is that you end up having to do tuning of this. Window scale tuning is a bit of magic kind of, or an art is probably a better term, because the larger you make the window, the more memory you have to have. So if we were to say make a the window scale of 14, where you can actually have 1 gig of unacked traffic, we would have to have enough memory in our machine to support 1 gig for every socket that we have. We don't have enough resources for that, and you guys probably don't have enough resources for that. Those are for really specialized high throughput links that they set the window scale that large. So you have to get the scale right. Window scale of 6 is about right for most use cases. You can set it higher, but it's something that you guys need to, and have your engineers be aware of, is that one, make sure that it's turned on, that you have it enabled. Most OSs today do, and consider that getting the window scale right to get good bandwidth through to S3. There's one more thing, I jumped wrong page. One more part about the TCP window scaling, or TCP transmissions, and that is that on the internet, packet loss happens all the time. Whether it's, and when it does, that data has to be retransmitted. This is the reason that we have TCP, or the windows, is so that the transmitter can store the data and have it available for retransmission. So in classic TCP, we would only acknowledge the data up until the byte that we had received. If we miss a packet, we stop acknowledging any more data. And so this can essentially stall the connection, and it causes the transmitter to retransmit the data. So again, the TCP, the IETF, the Internet, task force, came up with a standard for solving this problem. They call it selective ACK. And what selective ACK does is it allows the receiver to acknowledge parts of the stream. And by doing that, then when the transmitter sees that, hey, he's sending me a selective ACK, he knows specifically in this case, he would only send the bytes 1,000 through 1,100 back to the customer. And so you get better utilization of the pipe, and you don't have to retransmit a whole bunch of data at the same time. So most modern OSs do have selective acknowledgements turned on, but you should check, because it will make your bandwidth utilization much better. So today I kind of took you through these 10 procedures that you could use for making or utilizing S3. The key ones here, again, are the key hashing. For those customers who are putting a lot of data away, you need to consider the hashing technique. Bucket policies for both object expiration and the archiving are both something worth exploring. Multipart upload for better bandwidth utilization, and the ability to send really large objects with multipart. I believe I didn't say, but you can store up to, I believe it's 50 terabytes for a single object. Object aggregation, if this use case will fit your use case. Content distribution, consider using CloudFront with S3. End user logging, please turn it on. It's another thing that you might want to consider with end user logging is utilizing the Glacier, the object archival. So you can just take these end user logs, set a policy, move them off to Glacier. You'll have the data. If you ever want to go back and look at what was happening or do your own analytics on it, it's a great way to keep that data. Bucket policies, we just talked about today examples of using bucket policies for scaling up uploads, but there's a lot of other things that I suggest if you look at, that you can control things like what IP addresses customers are coming from, what time of day even they're making the requests. The bucket policies have really rich features, but today I just wanted to talk about it in the context of scaling for big applications. The same thing with pre-signed URLs. Any URL that you send to S3, you can generate a pre-signed URL. It's really good, again, in this context for the upload case, but you can also embed pre-signed URLs for getting content out of S3. Different use case, but you don't have, you can keep your data private, hand out the pre-signed URL that expires after a certain amount of time, and get there, and not have to grant access to your resources. And then finally, we talked a little bit about the DNS options and networking options. Let's see. So with that, it's kind of all I had today. And I thank you for taking the time to listen, and hopefully you guys have picked up 1 or 2 points that you'll be able to utilize when you build your apps on S3. So thank you.